be talking about optimal rates for averaged stochastic gradient descent and the neural tangent kernel regime. In this talk, we consider regression problem with the scale loss, and we present a convergence analysis of averaged SGD for overparameterized two-layer neural networks under NTK regime. The key assumption is the specification of the complexity of the target function and the hypothesis space. Under such assumptions, we derive an optimal convergence rate of the generalization bound on the iterates obtained by ASGD. Here, theta t is an iterates of ASGD. 0 is the base rule that is the optimal solution over all measurable functions, and R and beta are parameters used to describe the assumptions. In this setting, t corresponds to the number of examples used to obtain the hypothesis, so this equation provides a rate of generalization bound. Moreover, I note that this rate is always faster than 1 over square root t. The problem we would like to solve is the expected risk minimization with a square loss, and the hypothesis function is a two-layer neural networks taking this form. M is the number of neurons. AR and BR are parameters for output and input layers. Here theta represents a collection of all parameters. As you may know, the optimization problem of neural networks become non-convex, which is generally difficult to solve. So fundamental question in the context is what are conditions under which the global convergence and generalization are guaranteed. One promising idea is mapping the optimization dynamics in parameter space to function spaces and exploit the convexity of loss with respect to the function. Indeed, the loss is actually non-convex with respect to parameter, but it is convex with respect to a function as seen in this inequality. This is a reason why it's better to consider optimization in function space. Moreover, generalization bound can be also derived by characterizing a solution in this function space as done in our study. For this purpose of mapping optimization dynamics into function space, recently proposed neural tangent kernel and mean field view of optimization and overparameterization are very useful. Although we skip the detail here, in this study we focus on the NTK approach. Here, I briefly review the neural tangent kernel and explain its usefulness. Consider empirical risk minimization and run gradient descent for this problem with learning rate eta. We take the second-order Taylor expansion and substitute gradient descent update into this equation. Then we get this inequality with small learning rates. We see that unless theta t is a stationary point, gradient descent decreases the objective by this gradient norm. To measure the gradient norm, NTK is very useful. Neural tangent kernel is a type of kernel depending on the parameter of neural networks, which is defined by the inner product of derivatives of g theta of neural networks like this. Let the capital K theta be the gram matrix on n training data examples, xi, and v theta be a functional gradient defined on these examples. Here, functional gradient is a bunch of derivatives of loss function with respect to output of g at each training examples. So then the gradient norm is measured as a norm of functional gradient using the gram matrix k theta. So NTK is very useful in measuring the gradient norm. So if the gram matrix of NTK is positive, then the norm of gradient nabla L does not vanish because this lower bound holds. And the lower bound does not vanish at non-optimal functions. For instance, in the case of scale loss, the lower bound becomes the product of the minimum eigenvalues of the gram matrix of k theta and objective values. And combining this with the previous inequality, we get an exponential decrease of the loss function, like this. This implies that as long as NTK is positive, gradient descent converges to the global minimum at exponential rate. In fact, several studies show that overparameterization makes the gram matrix strictly positive during the training and shows a global convergence at exponential rate for regression problems using the square laws. Moreover, since the overparameterization is a localization of training dynamics, we can obtain a generalization bound via the Rademacher complexity analysis. Here is a generalization bound obtained in previous study. In this theorem, gradient descent is performed for t iterations, and for sufficiently large t, this bound on the expected risk with the square laws was obtained. Here, y1 to n is a vector of teacher labels, and h infinity is the limit of the gram matrix K at initial point. The limit is taken with respect to the number of training example n. With respect to the network width. The second term here converges to 0 as the number of examples goes to infinity. In order to show the convergence of the entire right-hand side, we consider the convergence of the first term here. In other words, to derive a convergence rate from this bound, we should consider the rate of numerator yh inverse y with respect to the number of training example n. However, unfortunately, the gram matrix H will degenerate in general as n goes to infinity, which means a slower convergence rate. Indeed, such degeneration is theoretically and empirically observed. This figure depicts the eigenvalues of the gram matrix of NTK on n training examples, and we observe a quick decay of eigenvalues. Here is an intuition on how to derive a reasonable convergence rate. If the vector of labels y lies in eigenspaces of the gram matrix H associated with large eigenvalues, then this value yh inverse y takes a small value, yielding a good convergence rate. So there is a possibility to derive a convergence rate as long as the target function is well specified using NTK. In other words, we should specify the eigenspaces that mainly contain the target function to obtain convergence rate. In summary, our question is, can we obtain a fast convergence rate with appropriate assumptions on the target and hypothesis functions? And we answer this question in this study. Here is a brief overview of our contribution. We aim to minimize the expected square loss. And the problem is equivalent to approximating the Bayes rule, which is a minimizer over all measurable functions. To do so, we run the single pass ASGD in which a fresh sample is observed and used to compute a single stochastic gradient and each iteration. For ASGD, we obtain this convergence rate, which is faster than 1 over square root t with the overparameterization. Here, t is the number of iterations. This means the convergence of ASGD to Bayes optimal. Moreover, t also corresponds to the number of examples used to obtain a hypothesis function. So the obtained rate of ASGD is the rate of generalization bound. To describe an assumption, we provide some notations and introduce the integral operator of NTK. Here, K infinity is an NTK with infinite network with two-layer neural networks. This kernel is multiple kernel consisting of the sum of two kernels corresponding to the output and input layer. So this indicates the multiple kernel learning aspects of learning two-layer neural networks. Next, we define the integral operator sigma infinity on L2 space weighted by the marginal distribution on X. The definition is here. So this operator can be considered a limit of the gram matrix of NTK with respect to the number of examples appeared in previous NTK theory on empirical risk minimization problems. Moreover, we note that the operator is a type of smooshing. of f because the function value of sigma f is simply a weighted sum of f using the kernel k infinity. Let mu(i) and phi be pair of eigenvalue and eigenfunctions of the integral operator mu, and mu(i) is sorted in decreasing order. Then the power of the integral operator along basis is defined like this. This power is naturally extended to the entire L2 space by taking linear expansion of this. In general, eigenfunction of small eigenvalues correspond to the high frequency of functions. So high frequency relatively vanish by the power of integral operator if R is large. In other words, the image of the power of the operator is composed of smooth functions with respect to the neural tangent kernel, and R controls the smoothness of the functions contained in this image. And then RKHS of NTK is represented as the image of the square root of sigma infinity, like this. Moreover, from this equation, so the faster decay of eigenvalues means a smaller RKHS because this condition is getting stronger. Here is main assumptions in our theory. The first is the smoothness of base rule. This says that base rule is contained in the power of the integral operator with R. So this assumption controls the smoothness of G law as explained. The second determines the decay speed of eigenvalues of integral operator. So this controls the size of RKHS. This is more formal version of the main theorem. Under appropriate assumptions, we obtain this convergence rate on the expected risk achieved by ASGD. A major difference from the informal version is an appearance of the term epsilon. Epsilon is a gap between learning dynamics of neural networks and its projection onto RKHS. This value can tend to 0 as m goes to infinity. In addition to this, the maximum number of t we can take also depends on the value of m. Hence, this theorem says that this rate can be achieved by the ASGD if the number of neurons is sufficiently large. I again remark that this theorem provides the rate of generalization bound, which is faster than 1 over square root t. Moreover, this rate is known to be the minimax optimal in this learning problem setting we consider. Here is a summary. I briefly reviewed the NTK theory and explained that the specification of the target function with NTK is useful for deriving a reasonable rate of the generalization bounds. Based on this intuition, we develop a new theory and derives an optimal convergence rate for ASGD. In addition, we empirically observe the slowdown for overparameterized neural networks in the misspecified case in the experiments on single-layer versus two-layer learning, although we omitted it in this presentation. So we guess this slowdown is because NTK should move in order to fit the target function, but it is almost fixed by overparameterization. So one interesting future direction is investigation into the misspecified case without overparameterization. So here I finish the presentation. This is a reference. Thank you for listening.